My name is Alli. I'm here to present a paper titled Method of Solving Multi-Area Economic Dispatch Problem. Actually, it's a survey paper, and we also propose a candidate SDP solution. The meaning of the SDP is Semidefinite Programming Approach. So I'm a staff in the University of the West Indies, the Faculty of Engineering. So before I begin my presentation, I would like to shed a little light on the word computational intelligence. The word computational intelligence has to do with the use of artificial intelligence to adjust the power system control in order to obtain optimum minimum objective functions, and at the same time to obtain optimum power flow. So basically, our major concern when it comes to economic dispatch, it has to do with minimization of the fuel cost of running power systems while satisfying all the system constraints. So the major concern about economic dispatch, it has to do is center on the use of minimization of the fuel cost. So this particular paper will be looking into the multi-area economic dispatch problem. So normally in minimization of power systems operation, the attainment of the minimum cost of power production is also can be accomplished by interconnecting power systems located in different areas. So also the topology of this power system network can either be a single area or multi-area network, depending on the size of the electrical power systems. So we have some benefits of power system connected in multi-areas, which are: it ensures optimal dispatch scheduling, and it also have this, it ensures low power deviations, and there is this possibility of this transfer of energy from one station to another using tight line capacity. So this work was prompted as a result of limited number of researches that has been conducted on multi-area economic dispatch. A lot of published work has addressed multi-area, multi-objective economic dispatch problem on a single area network, but only few have been able to consider multi-area economic dispatch problem. So we hereby propose an improved candidate solution in solving multi-area economic dispatch problem in order to address the limitation in some of the existing techniques. As for the method involved in solving multi-area economic dispatch, majority of this method, they are meta-heuristic algorithms. Some of them are evolutionary algorithms, and they have been used in attaining a feasible candidate solution. But due to the randomness in all these algorithms, the attainment of the ideal optimum solution are not guaranteed, as they require multiple runs and different solutions are obtained in each of these runs. That is, whenever you continue to run these algorithms, you continue to obtain several set of solutions over several runs. It will involve us to start keeping statistical data by looking for the best optimum value and the worst optimum value. So, and the ideal optimal solution is not guaranteed in this case. But as for the semi-definite programming, is a convex optimization techniques, not a population-based algorithm. And it has been used in attaining a single global optimum solution over several rounds if the problem is convex and the realization is tight. So even if non-convex problem, even for non-convex problem, semi-definite realization of this problem can be converted to the convex equivalent of it, and in order to achieve a computable band for the problem. So we have some of the existing publications in line with the algorithm involved in solving these multi-area economic dispatch problems. So we can see the abbreviation, though I'm unable to, if you're able to see the full papers of this particular presentation, you'll be able to get the full meaning of all these abbreviations correctly. So all these other methods, they are meta-heuristic algorithms, as we can. Also, all of these are meta-heuristic algorithms, and we can see that SDP, only few attention has been paid on the use of SDP in solving multi-objective, multi-area economic dispatch problem. So the objective of this study is to, the objective of this study is to review some of the existing work on single area and multi-area economic dispatch problems, and also to investigate on the approaches, the optimization techniques for solving multi-area economic dispatch problem. And at the same time, we also investigated the effect of tight line constraint, and when the network is not incorporated with tight line, when the power network is not incorporated with tight line. So we also propose an improved candidate solution for solving this multi-area economic dispatch problem. I'm sorry, this is too large, unfortunately. So as for SDP, SDP is a convex optimization techniques that is used to minimize objective functions subject to some combination of symmetry, which has positive semi-definite. Sorry, hello, the organizer? Hello? Sorry, yeah, I think
you can hear.
Yes, we hear you.
The resolution of this slide is just too high, I don't know. So I think I have to, there were some loss of information which I think I'm getting from here. So in terms of, I have some information here. So apology, I have to maybe look for alternative to. Try to. I think this guy is a little bit better. I think this example. Can you see this, please?
Yes, we can.
Thank you very much. I think this is the exact PowerPoint which I was trying to upload initially. So.
Okay.
Unfortunately, okay. Actually, I have something missing. I don't know. Maybe the PowerPoint was disarranged when trying to upload. So normally, what is concerned about this use of semi-definite programming, it has to do with whenever we have our objective function, if our objective function is not in convex optimization problem, so it will be very difficult for our algorithm to solve, and ideal optimum solution is not even guaranteed when your problem, when objective function is not in a convex form. So I have some information missing as per the methodology. So let me use these two charts. We can all see that from these two figures, the figure on the right side of the equation we can see is a non-convex problem. So, and it will be very difficult for algorithm. If I may ask everybody that the two functions that we can see, the left side is it will be more easier to solve compared to the one at the right side. So the one at the right side is a non-convex. So we have at the left side, which is convex. So this is actually what a semi-definite is going to do. We need to convert any problem in out of convex, which is probably non-convex or linear problem. We need to convert it to a convex problem, which we can see by the left side of the equation. So basically, our procedure in our subsequent paper, it has to do with we're going to consider a bi-objective function subject to some constraints, which are equality and inequality constraints. And these problems, both the objective function and the constraint, will be converted to the SDP format by relaxing these problems. So also both the objective function, and the constraint will also be relaxed. And this SDP relaxation will be passed to SDP parser, which is C-domain. There are some two boxes involved that actually help us to convert this. The format that we have this SDP realization is initially a premium solution. So we need to convert this set of problems to a dual form, because the solution obtained from a premium solution is going to give us a weak solution. So there is necessary for us to convert this problem to a premium, to a dual form of semi-definite objective functions. So finally, we obtain our optimum solution from our objective functions. So we have some preliminary, the analysis and simulation which were conducted. We plan to conduct simulation on IEEE 4 area 16 units network, and also on IEEE 4 area 40 units networks in order to validate our algorithm. So also there are some other information which we're also missing from here. I really don't know why this is happening. We also plan to compare the results to investigate different cases when the system is incorporated with tight line transfer capacity and when the system is without a tight line transfer capacity. So in order to validate our algorithm as well. So also this particular method, the result obtained from the objective function, from the minimum objective function, will also be compared with some of the existing method that has been reported in the literature review. So we have some preliminary results that I would like to show us here.
Okay, Doc.
Yes. I'm almost done, just few slides. So maybe like two slides before the reference. So I have this preliminary studies here. When we consider a 16-unit network, 4 area network system, these are some of the optimum power that are generated. Like I said, the main targets about economic dispatch, we are focusing on minimization of the fuel cost. So you can see that when the system is incorporated with tight line capacity, we're able to obtain minimum value compared to when particle swarm optimization is used. So we can see these two results. So in a case when the tight line is not incorporated into the optimization module, there is this little drop in the fuel cost. So compares to the optimal value obtained from the particle swarm optimization techniques. So these are some of the preliminary results. We have the result obtained, the Pareto form results obtained from the use of SDP compares to these evolutionary algorithms. We can see that at a certain time, we're able to obtain some minimum fuel cost compares to when we have these other algorithms. So I'm so sorry, I have some of the references, but full details of the references are in the full paper. So I want to use this moment to apologize for what have happened. I want to welcome any questions as regards to.
Okay, thank you. Thank you, Dr. Alli.
Yeah, you're welcome. Yes, sir.
I understand the technical difficulties, but the presentation was great, very informative. I believe that we have a question, but I would rather be waiting for the questionnaire to be just contacting you by email. Okay, thank you.
Yes, I will definitely make my email available. So.
There will be a lot of questions. It's a nice presentation. Okay, appreciate your time. So,
you're most welcome.
bye. So I am now going to